Hello, this is the first video in the series that will cover the BOLT11 spec and walk you through creating JavaScript code to break down a payment request and to help you understand what each of the parts mean and how to translate them into something useful. To show you what that looks like, here's an example page I made that basically does what we will be trying to accomplish in this tutorial. We will take a payment request like you see in the text area and we'll parse it into the JSON format like you see at the bottom. As you can see, this page breaks down a raw payment request in what is known as the BEC32 format and translate into something understandable. The JSON that we will create in this tutorial and additionally a color-coded visual. Each color represents a unique piece of the data encoded into the payment request. So you can see here that the color-coded, if I hover over a section of it, I get an indication of what that is. So I hover over this first orange colored piece and it tells me it's a prefix. I hover over the next one, it tells me the amount. Next one in blue, the separator, etc., timestamp. You can find the BOLT11 spec at the lightning-rfc repository. I have it pulled up here, and basically the BOLT11 is, well, there's two sections to it. There's the human readable part and there is the data part. The human readable part is everything before the blue one that I showed you on the previous page. So you can see the blue one here. Everything before that is a human readable part. Everything after that is your data part. As you can see here, the human readable part consists of a prefix and an amount. So if we go back to the other page, we can see the orange is the prefix. LNBC means it's Lightning Bitcoin, and the 25 micro means it's 2,500 micro Satoshis. The data part consists of a timestamp, 0 or more tag parts, and a signature. So we can scroll down to the tagged fields here and take a look at what that looks like. You have 5 bits, which tells you what type of field it is. You have 10 bits that tell you the length of it, and then you have the data itself. Now, to get from the cryptic encoded non-human readable part, we need to take a look at the BEC32 encoding. So I have it pulled up here, and you can see from the chart that you have the numbers across the top, and then you have, the adders along the left-hand column. So if you're at, Z represents 2, and if you go down like to the next row, like F would be 1 plus 8, so it would represent 9. So we have basically 5-bit words here that are consisting of these 32 characters. That's where you get the 32 in the BEC32 from. So now going back to the tagged fields, we can look further down. We can see that, like, for example, P is the pre-image represented by the number 1 once we translate it, and it's of a 52 word length. D is for description, and it's represented by number 13, and the variable length because the description, could have how many ever characters up to the limit. So to illustrate what needs to be done, I made this chart. What we want to do is take the 32 characters, which are represented by 5-bit words, and convert them to 8-bit values that are more familiar, whether you're using them as a string for a description or a hex representation for a payment hash, signature, etc. You can see on the top row, everything is divided into 5 bits, which would represent the BEC32 format, each of those being a BEC32 word. The byte format is more familiar. It's represented by 8 bits. So we can see we start with the first word of the BEC32 format, and that's in red. That would make up the first 5 characters of the byte format. And then 5 bits, excuse me. And then the second in green, the second word of the BEC32 format we would take the first 3 bits to complete the first byte, and then take the next 2 to start the second byte, and then we continue with blue, etc., etc. We take that, but we're still one short, so we take the gold colored from the 4th, etc., etc. So the first thing we're going to need to do is create a reader that will translate that BEC32 5-bit format into the 8-bit byte format. Okay, so now we have some background in place. We can start coding. We're going to create the project and create the reader class to do the conversion from 5 bits to 8 bits, and we're going to create some tests that will help us verify that. So let's create the project, and we're going to stick to conventional JavaScript format. So I'm going to come over here, make a directory, BOLT11. We'll just leave it at that. We'll change into it. And we're going to make a source directory. And a test directory. Okay, so now we're going to initialize a project. And we could just take all the defaults here. We're not really doing anything special, just a tutorial. So now we have it initialized for npm. I'm going to install for the test, I'm going to install bmocha. Most people are familiar with Mocha, but I'm kind of a minimal dependency kind of person, and bmocha is from the Bitcoin project, and it does not have any dependencies. It's a standalone package, so I use that. It's compatible with Mocha, but it is a way to break free from the JavaScript dependency hell clusterfuck that we all know and love so well. So here we go. It's a development dependency. We're just running tests. So oh, we have one package from one contributor. How refreshing. Okay, so I got VS Code up and running here, and what I want to do under my source, I'm going to create the reader file, reader.js. And what we want to do first is create the reader class. We'll call it word reader. And what I'm going to do is create the constructor, which is going to take the BEC32 words, and I'm going to need some values for keeping track of where I am. So I'm going to have an index, and I'm going to store the words themselves. So I have the words, I can index through them, and so we're going to initialize those. This dot index equals 0. This dot words equals words. So if you remember from when we looked at the tagged data fields, we started with the first 5 bits told us what type it was, which is an integer, and the next 10 bits told us how long the data was. So we're going to start by reading integer values from it. So I create the readInt function, and we're going to take n as a parameter. That's how many bits we're going to read. So we need a starting point. We're going to start at 0, and as we read the bits, we'll calculate up to a value that we'll be able to return. So the next thing we want to do is create a loop. We want to loop n times. So now we're going to have to keep track of two things. Remember, we have the words from the BEC32, so we need to keep track of which word we are on, and we also need to keep track of which bit we are in that word. So we're going from 5 to 8, so we need to know, like when we're in the first word, we got 0 to 4 as our index. And then we go to the next word, we're on word 1, we start at index 0 again, 1 and 2. Then we finally have a byte. So we need to keep track of where we are, which word we're on and which index we are in that word. Okay, so the word index is pretty straightforward. We are taking the index and dividing, not modulus, we're dividing by 5. Oops, dividing by 5. So, 0, 1, 2, 3, 4, the first 5, well, that would all floor down to 0 divided, you floor down, you're going to be at word index 0. Then once we get to 5, 6, 7, 8, 9, we're at word index 1. Pretty straightforward there. Now the bit index is a little bit more tricky. We are inverting that because if you're reading from left to right, you have 0, 1, 2, 3, 4. The fourth bit will have the least value. So what we're doing is taking 2 to the nth power. And so if we start with the fourth bit, that would be the one of the least value. So we're just going to take the modulus, but then invert as we go. So wherever we are in our index, we invert that, and that will be our bit index in that particular word. So we have our word index. The next thing we want to do is use that to get our word. So now we have our word, but remember we're looping through, so we need to know what the integer value is of that particular bit in that particular word. So if we're reading like 10 bits, we're reading 2 words. So if we're on the very first digit, that's going to be the most value, the largest value representation. So what we need to do, everything is 2 to the nth power when we're looking at bits. So we need to take whichever bit we're on, figure out where that represents in the 2 to the nth scheme of things, and we need to add that to the value we created at the very beginning, the val value, which is 0 before we start looping through. So what is all this nonsense? Just like I'm anal about low dependencies, I'm also anal about doing things the correct way, as opposed to a lot of people in the JavaScript ecosystem are kind of anal in the other direction about making code readable. I'm kind of anal in the direction that, well, if the code's not readable, you learn to read it, and it's only something you have to do once. So I'm going to explain this non-readable code, and once you learn what all the parts of it mean, well, it should be readable the next time you see it. So basically, anytime you are taking 2 to a power, the nth power, you're basically shifting left. Because if you remember your binary, you start with 1, 2, 4, 8, 16, etc. That's what each of the individual bits represent. So by shifting left, you're going to be multiplying by power, and that's the most efficient way to do it. And everything I've seen implemented does this also. So it's not everybody that's anal about it, but this is the correct way to do it, although less readable. So what we're doing is we're taking 1 and we're shifting it however far we are in the sequence, but inverted, so we're going to start at n minus I minus 1, because we want, if we're on the very first bit, we want it to represent 0 because we don't want to shift at all. And then you see the multiply word and the two arrows pointing to the right is a right shift by the bit index. Where are we in that word? And then the ampersand 1 is your AND operation. So what we're doing is, if we're like, on the second bit or whatever, we're going to take the word and we're going to shift over the bit index, but remember it's inverted, so however far we shift over, and when we mask it with a 1, we're either going to have a 1 or a 0. So if we're on, for example, like, the bit that represents 32, but once we shift over and we mask with 1, if it's 0 and 1 is going to amount to 0, so we will multiply, we're going to have a 0 there. But if we shifted over and masked a 1 with a 1, well, that would be 1. So we're going to multiply our 32, and then we're going to add it to the power. And then next we will actually add it. Val plus equals. And we also wanted to keep track of where we are in the individual reader itself. So and once we complete the loop, we should be able to return our val and be done with it. And of course we want to make that available, so we need to export it. Okay, now we should be ready to go. We're going to test it. Before we do that, we have to set up our package.json to use the bmocha that we set up earlier. So okay, now that we're all set up, let's create a test. Okay, now let's run that and see how we did. There we go. One test passed. So what we have here is an array of the values 1, 1, 2, which is our 5-bit 32-word representation, represented by that number in the comment there. And starting from the right, you got 1, 2, we got 2 plus, going over, we got 32, and we got 1024 adds up to 1058. So I called the reader read-in of 15, and I compared that value to 1058, and it passed. Okay, so let's add a few more tests and see how we do. Okay, we're good to go. Okay, and also, as if you'll remember when we looked at the type length value tagged fields, that we read 5 bits for the type and 10 bits for the length. So let's add some tests to read in sequence. Now let's save it and run it and see what happens. Okay, 2 tests passed. Okay, so now that we have integers working, we have that third piece of data in the type length value fields for the tag fields. So, which is just, whatever that length value is, that's how many words you got to read in. So that's what we're going to do next. We're going to read words. So here all we're doing is grabbing n words. So we figure out our word index is where we are, and n times 5, since each word is 5 bits, is where we want to end up. So we add that to our index before we return, and then we slice from our word index to our word index plus n. This really doesn't give us any translation, but we're going to do this in 2 steps. First, we're going to grab the words, and then we're going to translate them based on whether it's going to be a hex or a UTF-8 word. So now we have the words. Let's try and make some tests for those. This one hopefully should need little explanation. We're just slicing it up. So if we read 2, we're getting the first 2, which is 1 and 2. And then we get the next 4, which is 3, 4, 5, and 6. That part's pretty straightforward. So the next step would be to, once we have it to the slice, translate it. So I'm going to come back over to the reader file here. We're going to create a read function that will just read bit by bit. So up to this point, we created the read function. It's very similar to the read int. You're going to read n bits. And there's also a pad parameter that's, if you're, since we're going from 5-bit to 8-bit, we might have some, only get 2 of the 8 bits. We want to be able to fill in the rest of that with zeros, so everything will still line up on a bit-by-bit basis from the 5 bits. So, and we also added a response value, which is an array, which is going to be our target bits. Now we're getting to more what I showed you in that one chart with the colored, with the 5 and the 8. So the first part of for loop is identical. So let's finish the loop out. Okay, now we're doing something that should be readable to you by now. And it's similar to what we're doing with the integer, except for the integer, we just kept accumulating the value the whole time. Here we want to accumulate until we get to 8 bits, and then we want to push that to our array. So that's where the difference is. That's why you have that, 7 minus I mod 8. That's keeping track of where you are with I for how many to shift. But then down below in the if statement, if I mod 8 equals 7, that means, remember, we got 0 through 7. That means we're on our last bit of the 8-bit word. Then we push it to the array. And now for the padding, what we're doing is we're seeing how many bits are left over. And if there are any bits left over, what we're doing is shifting left by that amount of bits and masking with 255 to keep us in the byte range. And we're doing that right here. I'm doing it to the last word, but I'm realizing that that's not correct. It just happens to work because what I'm doing is, when I was doing the slice words in the previous step, the read words function, and I was passing that whole thing to the read function, but really, let me fix that. Okay, so let's test this. I have a test. I'm just going to paste it in here. And that did not work. And if we go back to our reader, we can see that When we come here, we're pushing the value, but once we do that, we need to reset our value or it keeps accumulating. So that's what the problem is here. So now let's give it another try. And we're good to go. Okay, I'm going to add one more test, which is kind of closer to a real world kind of test. So you can see from the translation table up above is the one I already showed you from the VEC32 spec. And we look at our values. I create an array of, for that string value of QQQ. These are values from the BOLT spec. So QQQ is going to be 000 based on the chart. So that's the first. And S translates to 16, etc., etc. That's the value you're going to start with. And the expected value from the test vectors is, 0, 0, 0, 1, 0, 2, 0, 3. Kind of an odd value, but that's what they made up for testing. So it would translate to that B256 array, 0, 1, 2, 3, and it keeps repeating, except for it's a little bit different at the end. So let's save that and run. And we can read our hash value, so closer to real world there. And that's it for the reader part. And next time we're going to, in the next video, make a decoder, which will actually take each of the different things that we read in and make them something useful that we can finally make our parser out of that. So we will see you then.